This video is going to review bonding and transition metal complexes that you had in previous courses. We're going to start off with, again, all be octahedral. We're going to look at sigma bonding. An example may be cobalt with 6 ammonias. So what I have here are the metal orbitals. And obviously we have the 3 d orbitals, and we have a 4s and 3 4p orbitals, and their relative shapes are shown here. So there are 3 of these particular orbitals, dxy, dyz, and dxz. So now let's look at add the ligand orbitals. Now we're going to have to come up with 6 ligand orbitals because we're going to form six bonds, essentially, to the metal. So here they are. And if you think about it, the ligands will have 6 orbitals. They're shown here. One is sort of considered like an s orbital, 3 p's, and 2 d orbitals. And the p orbitals, again, there are 3 of them, and the d orbitals would be the equivalent of like dx squared minus y squared and dz squared. So these would be Eg orbitals. Because if you think about it, there's only going to be 6 bonds to the metal, and 2 of those bonds will have to interact with the Eg orbitals on the metal. So let's see what happens when we bring these together. And note, of course, these orbitals are lower in energy for the ligands than the transition metals, because we're talking about maybe 3d electrons and 4s and 4p. So let's bring them together to form some MOs. So we're going to form MOs, and I think you can see that with the lowest MOs are going to be bonding, and then we're going to have anti-bonding and some non-bonding. And the bonding ones would be between, for instance, the 4s and the A1G, which is S-like. And then we're going to have 3 T1U orbitals, which are equivalent to interactions like of the 4p with like the p orbitals on the ligand. And then the metal orbitals, there are the Eg orbitals. What we're going to have are 2 of those, the dz squared, dx squared minus y squared, can interact with the Eg orbitals from the ligand. So again, we have these 6 bonding MOs. Now what's left over are the T2Gs on the metal, so they're going to be non-bonding. Let's say there's no electrons in them, so they're non-bonding. But of course, as we use the the 2 Eg orbitals, and those are shown here, okay, the dz squared and dx squared minus y squared, because we use those to form the bonds with the ligand orbitals. We have the Eg bonding orbital down there, but then we're going to have the Eg anti-bonding orbitals higher up. So, I mean, a lot of people just consider these as just the ligand orbitals, but remember the top 2 are the Eg non-bonding orbitals. Now, of course, when we, if we want to put energy in, and if we did have electrons in the non-bonding T2Gs, and then we would put a little energy in, we could promote them to the Eg anti-bonding, and that's the delta value of the field, the splitting energy between the T2Gs, which would be non-bonding, and the anti-bonding Eg. So that's the case when we have sigma bonds, 6 ligands interacting with a metal cell in octahedral geometry. And I think hopefully that should make sense. Now, in some books, I've actually seen the nature of these orbitals altered a little bit, so that sometimes there's a switch between the T1U, like the equivalence of the P and the A1Gs. Yeah, so that's something that I've seen. I'm not exactly certain why, but those switches are sometimes seen in books.